Okay, so now we finally have our result on the perturbed power pattern. We're saying the expected value of the power pattern, or the beam pattern, how much power it would let through from all these different directions, is the nominal one, the one we thought we had for the ideal array, times attenuated by this factor here, e to the minus k naught squared sigma p squared, where again this sigma p squared is the variance of the sensor position error, plus another term that is just independent of k. So this is true for all directions, that I add in a term that's like the magnitude of w squared, 1 minus e to the minus k naught sigma p. So it's worth taking a moment to interpret a few of these things. If I think about k naught sigma p, I can write it like this, and maybe converting k naught back into 2 pi over lambda times sigma p. What this is saying is this standard deviation of the sensor location error in meters, I'm going to divide it out by the wavelength. It has to do with how big is this error, this sort of typical error, standard deviation, relative to a wavelength, where one wavelength would give me 2 pi of radian change. So it's sort of saying, on average, how much is that perturbation, how many radians is it going to cost me in phase? How far out of alignment are things going to get? So this is sort of convincingly unitless. In fact, this is useful enough that Van Trees calls this sigma lambda squared, saying it's the variance relative to a wavelength. So in the Van Trees book, they call it that. And so if I think about what's going on here, if I thought of like on a dB scale, an original nominal beam pattern like this, I'll just draw the right half. So imagine this is the magnitude of b squared in dB. So I have this peak at 0 dB, and then things are going down. What this is saying is that I'm going to get this thing, the perturbed version, the first term here would be like just slightly attenuating this thing, moving it down a very little bit. Right, subtracting a small amount from it. And then the second term, maybe I'll treat that second term as blue here, is independent of k. If this is my kz axis or whatever, it's saying I'm basically adding a constant to this. So I'm sort of filling in the valleys. That what we're going to be really, what might have been ideally, really, if I drew it carefully here, really deep notches are now getting filled in by this blue thing. So when I'm adding these two, when this one's big, this doesn't matter much, right? This isn't mattering much, but it's saying that basically when I go into the notches and this nominal beam pattern would be going down to 0, this term becomes the dominant term, and it says I'm sort of filling in those notches. So there's a limit on how deep, how much destructive interference I can get, like we expected from our conceptual discussion at the start, based on how much variance I have in this perturbation. And in fact, looking at these are just, aren't they just so tempting to do Taylor series things too, right? We can just say, what if those things were small? We could simplify things, right? It's just hard to resist. So I'm not going to resist. We're going to look at this and say, well, how can we simplify that further using Taylor series? Right, so what do we get for Taylor series? Well, if this variance normalized to a wavelength, so 2 pi over lambda times sigma p squared is small, that is much, much less than 1, we can say that e to the minus sigma squared lambda is approximately 1 minus its argument, right? So it's going to be, e to the plus its argument, but since that argument is negative, it'd be 1 minus sigma lambda squared. And similarly then, when we have 1 minus that in the other term, it's just going to be 1 minus this. So that would be like saying that second term is approximately sigma lambda squared. So if I bring over the other side under these assumptions again, so if this is small enough, let me rewrite the equation here with the approximation. So when I've brought those terms over and converted it, saying I've now got again these two terms, part due to the original beam pattern I tried to design, is going to be attenuated just a little bit. It would be multiplied by something just a little less than 1 based on how much error I have in the element positions relative to a wavelength. Plus, I'll have sigma lambda squared times the magnitude of the weight vector. So the other interesting point here, right, is this thing keeps showing up. This is not the first time we've seen a magnitude of w squared, right? This is in fact, pause the video and try to remind yourself for a minute where you've seen that before. All right, now you're back, right? This is actually 1 over, right? We saw that the array gain against white noise was 1 over the magnitude of w squared. So this is telling me that the smaller this is, the better my array gain is. And so the smaller this is, the less sensitive I am to noise, the less I fill in the notches. So this is another reason we're always thinking about the magnitude of the weight vector squared. The bigger that weight vector is, the magnitude squared, the worse my white noise gain is, and the more sensitive I am to errors in my array element locations. And so that's a thing that keeps showing up that's very important. How much we're going to fill in those destructive notches is going to be more and more sensitive depending on two things, which is how much variance I have in the locations of my sensors, and how large the array weight vector is that I'm applying to the array. So we'll talk about some of the other interpretations now, but again, the main thing to remember is that the average power pattern of the perturbed array has two terms, one of which is the nominal power pattern we thought we were getting, slightly attenuated due to the errors, plus another term where we're filling in the valleys. And how much we're filling in the valleys depends on how much error we have in the sensors and how much the magnitude of the weight vector squared is. All right, so that's all for now. But that's sort of the big picture derivation. We'll talk about interpretations and examples of this in class tomorrow.